Hey everyone, thanks for joining us. I'm Ian Sayers. I'm a 3D scanning product manager with Hawkridge. I'm joined by Matthew Fisher, an application engineer who specializes in 3D scanning applications. So we normally talk about 3D scanning and directly related topics. And 3D scanning definitely factors in to the talk today, but it's only a small part of it. So we're doing something a little bit different this time. The central problem that we're tackling, or one of them that's heavily involved in this, is something we've covered before in the past, including at a previous D2M event, but in a slightly different context. So before, we dealt with the problem of working with organic shapes, and we showed you how to confront that with a technique called hybrid modeling in the context of scan-based design. But that only takes you so far. Hybrid modeling is a really good way to duplicate a shape, but it can't really help you design something original around a scan data. So that's what we're focusing on more today, is this issue in the context of scan-based design, designing an original object around scan data rather than duplicating the scan data itself. So to reiterate this problem, let's say that your boss walks up to your desk with these two parts in his hand, physical parts, and he says, I need you to take your calipers or whatever and reverse engineer me one of these two parts by the end of today and get me a CAD file of this part.
Hey, Ian, just jump in. Looks like the screen's not being shared right now. Don't
Oh,
know if it had a hiccup.
Let's try it again.
Perfect.
All right,
now we can see it. We're good to go.
Perfect. So we're looking at these two parts, and your boss has brought them to you, and he wants a CAD file of one of these by the end of today. And we all know, if we're SolidWorks users or whatever, we all know that we're going to choose the one on the left. It's just easier. The one on the right actually has fewer features, but the nature of the geometry and those features is harder to measure and harder to express in CAD. And there are several reasons for this latter claim. One of the biggest reasons traces back to around 35,000 years ago. This is when, according to anthropologists, some brainiac somewhere figured out that they could make a through hole by pressing a pointy object against a surface and rotating it. And by around 10,000 years ago, we start seeing pump drills and bow drills, the first machine tools, and we see drilling being used in dentistry. And by around 2,200 years ago, we start seeing people in China using drilling rigs or derricks to drill wells. And derricks, like a bow drill, allow the power source to move up and down on the drill shaft or vice versa, meaning that the drill shaft itself can be raised and lowered. So with that, it was only a matter of time before someone realized, hey, if I can raise the drill up and down while it's spinning, I can move an object around underneath the drill, and with those two axes of motion, I can carve out any shape without undercuts, that is, right? So needless to say, that was still a huge advance, undercuts aside, and it caught on like wildfire, and the rest is history. And ever since, we've been making the vast majority of objects, either directly or indirectly, by removing material with rotating bits. A lot of objects, well, more objects are molded, which adds its own set of similar limitations, but of course those molds need machined too. So this method, or these two methods, touch almost everything we do. And since these methods have certain limitations, those have been projected onto our design process to some extent or another, because after all, why would you want to design something that can't be manufactured? There are some other reasons why prismatic shapes are easier to design. They're easier to describe or express, and that applies equally to human brains and to the computer science behind expressing 3D shapes. So for instance, there's nothing on this bracket that I couldn't describe on a drawing sheet or even over the phone in 30 seconds. I might say something like, there's a 3-inch wide flange made a 1/4-inch stock. It goes for 6 inches, jogs 90 degrees to a 3-inch flange, which has a 1/2-inch hole centered 1 inch from the outer edge, blah, 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 right? And you can sketch out that part almost as quickly as I can describe it. It's pretty easy, right? But how would we go about describing parts like these? And again, this doesn't just apply to our human brains, it applies to computer science, which is, of course, emergent from our human brains. Expressing these shapes here mathematically just aren't as straightforward. So our limitations don't stop at the physical, at the manufacturing process. We're in this paradigm where the dominant way of expressing shapes is to describe the steps they took to become that shape, mainly by extruding, sweeping, cutting, and other simple commands. And that method of expressing shapes lends itself really well to prismatic shapes like the one shown here, or the bracket, or an engine block, shapes that consist of planes and cylinders and cones and other standard features, or what we might refer to as primitive shapes, or simply primitives. So this is the dominant method for a reason. It's relatively efficient, maybe not in terms of material use because we're cutting all this stuff away, but again, those shapes like the bracket are easy to describe, easy to design, easy to create with rotating cutting tools. And so it's dominant for a reason. It's still the best current fit for most of what we do, at least for now. But these shapes we see here, along with the topology optimized part that we saw a couple slides back, these kind of represent where we run out a road with traditional methods that have otherwise served us really well. And there's a strong drive to work with these shapes. That kind of prismatic geometry we saw, that doesn't work for ergonomics. It doesn't work for implants and other devices that need to fit or interface with the human body. And it doesn't help us with topology optimized parts like those ones a few slides back. But all this stuff is in high demand now. We can use those topo parts to make things stronger, lighter, and faster. And we can use more ergonomic parts to make more appealing products that work measurably better. And for the first time in, I guess, 35,000 years, we're seeing a really fundamental changes to the way we can create things. So over the years, we've just added on to the same basic approach. We added electric power. We added numerical control. We added more axes to our machine tools. But the fundamental way we make things hasn't changed in all that time. It just improved in increments. And all of a sudden, in the last 40 years, additive rather than subtractive manufacturing has matured into this genuinely viable manufacturing method. But for a lot of us, there's still a disconnect between our design process and the manufacturing process. Sure, we can print any shape we want in titanium, but can we design any shape, right? Some industries have a stronger drive than others to work with these shapes. And so they've been dealing with this conundrum for longer. It turns out that there actually are tools that are excellent for this type of work that just aren't widely known in the engineering design community. So we used one such tool in this project, a software called freeform that originally came out of the medical industry. It was intended for designing medical implants, prosthetics, and reconstructions, which of course are all very organic in shape. It's been adopted by various other industries that have similar needs for designing freeform shapes like toys and footwear, but like I said, it's largely unknown elsewhere. So in this study, we mostly used the cage-based sub-D modeling that this tool has, but it has a lot of other interesting capabilities like clay modeling with haptic feedback, organic texturing, and too many other cool things to get into today. If you have a need to work with these kind of shapes on a broad scale, go to the Hawkridge webpage, click on that resource center at the very top, check out our recent webinar on duplicating organic shapes. That goes more into depth on the entire range of tools available in it. So anyway, this tool allowed us to create the shapes we already had in mind. But I think the final destination in this case was the least interesting thing about it. It's great that we got from A to B and we can tackle these shapes that are in our imaginations that our other tools can't handle well. But what we found most compelling about this was the unexpected way that using this tool changed our creative process and let us approach the design cycle in a new way, and how we came up with forms that we hadn't planned on, just because the freedom of design that this tool allows. So with that, I'm going to hand it off to Matt Fisher, who is going to show us how all this went down.
Thank you, Ian. just gonna set it up, and there we are. You should be seeing my screen now. So thank you everybody for joining. As mentioned, I'm Matthew Fisher. I'm an application engineer here at Hawk Ridge. And to kind of expand upon what Ian's been talking about, we're going to be talking about a case study of designing a part. So the abstract of this is that we were given the task, the task is we were going to design an air spoiler for a Grand Tour car. If you've ever seen a Grand Tour car, it's a very sleek backside of it. It's got a very smooth backside. And it's very difficult to add products to it and kind of design around it because of just how freeform carved it is. So what we want to do is kind of approach it in a way of, hey, can we add something to something that hasn't been added onto before? In this case, the spoiler. And is there a way we can kind of do this in a rapid prototype type of way? And I want to just kind of lay it on the table there, saying that I am not an aerodynamics engineer. I have never designed a spoiler ever, and I've also never really used a simulations tool. So it was kind of just also a dive into how can we take somebody who's never really used these tools in these ways and get something out in the end, and what is the kind of workflow with this. And how we approach this is, as Ian mentioned, using this geometric freeform to rapidly prototype using some sub-D modeling on these spoilers. So what are the challenges with this model? Well, as I said, a Grand Tour car doesn't really have a trunk, so there's not really a mounting place for it. So we have to design around this idea of making a mounting fixture and then adding the spoiler to it. We also want to make sure we don't really impede any part of the car. So we have a couple limitations on the sizes that we can work with, but we still wanted a lot of space to be able to have our freedom go with our creativity. And as mentioned, we want to make something very unique without really compromising the airflow. So how we can create something unique and figure out how it interfaces with our object is through SolidWorks simulations, which we'll talk about later on. We scan this car first using an Artec Ava. It's a handheld scanner that we sell. Really great for objects of car, the size of a car. Very little loss in any kind of precision, if any. And we then converted that scan into a solid body, so we have something a bit more easier to work with. So the first thing I really want to touch on is this idea of sub-D modeling. We've kind of mentioned it already a few times, but haven't really gone into depth on it. And what subdivision modeling is it's the method of representing a smooth surface via the specifications of a coarser polygon mesh. And it sounds kind of weird, but really what it's essentially saying is we can create meshes of different objects and sizes and kind of push and pull them based on a cage idea of projecting all these different faces onto a center point, again calling a cage, and then subdividing those cages into a desired polygon count, creating our surfaces. And it's this projection method that allows us to create these extremely smooth transitions between different parts of the faces without needing to worry too much about tangential splines or anything like that. So in this case, on this little GIF on the right, you can see that I'm able to just push and pull 2 points around, and we create a really smooth transition between them, and it's automatically adjusting as I'm pushing and pulling. And this is something that in the traditional sense of CAD modeling, we'd have to have a series of different splines, and then these splines all stitched together in a tangential way. And then if we adjust one thing, how is it going to affect our down the line aspect of it? Whereas in freeform, I'm able to just kind of change the cage size, maybe make it a little bit coarser, move it around a little bit for big movements, change the density of the surfaces to make it more coarser if I need, to really create these freeform shapes. And this really plays in the role of spoiler design, and why we inspired to make a spoiler is because traditional spoilers, from what we've seen on the market, are made just like how I mentioned, with splines and tangential points and extrusions, whereas now we were able to just kind of hand carve essentially a spoiler to fit this car. And so designing in freeform actually is really easy. The real big steps are I took this car model, I imported it into freeform, I designed 2 brackets real quick just so that way I have a reference of how everything is size-wise. And at that point, I'm able to place my starter sub-D model into the proper position and begin sculpting or pushing and pulling with that sub-D model. And if I ever wanted to make a new design, all I had to do was just duplicate that initial starter sub-D model and start creating the extra designs with it off of that. And when I want to go back and make a second design version or another one, I can either duplicate that again. And again, I have all these cage settings so I can adjust the exact size. And this is something that, I'm representing in GIFs, but it's actually something that I'd like to really show more of a live demo on it. So I have freeform open right now. In fact, actually, I'm going to just show my camera so you can see exactly the tool I'm using, this haptic device tool. So I'm just going to push this down just a little bit. And right here, I have a haptic pen. This comes with, or it's used for freeform, allows us to give this a live feedback of our modeling process. So I go over back into my spoiler design. This is inside of freeform. I have a list of all of my models listed right here. My car is already in place, and I have my starter sub D. And how I make my next design is I just right click, go down into duplicate, and we can start away. I can name this something like design 5 and begin editing it. It's already activated. So I go down in my tree to sub D surfaces, and then I click on this edit sub D option. And you can see that cage starts to appear around it now. And from here, it really is just that pushing and pulling part of it. I can go up and start touching the model. And as you can see, my pin's actually kind of getting locked in place, letting me know I'm interacting with the object already. And if I start moving this around based off of a point, you can see only one side is moving. So to make something symmetrical, all I have to do is select on a control line, add a planar symmetry, and there we go. Now everything is symmetrical on itself. And I can even do this with multiple parts. So I can really make some crazy designs really easily. And as you can see, as I kind of move them closer together, really starts to just smoothly combine into one another because of that cage and surface factor. So just to kind of go through what I did with these different approaches, again, we wanted to approach this in a rapid design method, just trying to get an idea out there, get a lot of initial designs out so we can see really how we can improve upon them. So what I did for most of the designs is I would create the symmetry face, and then I would select on one part of it, and I can really just make these kind of large bulk movements to get some ideas going. So something like this, I'm going to maybe make it like this right here. Maybe I'll move this face out a bit more. And, it looks like the backside is, not interacting really well with the brackets. So here I go, moving that closer, making sure it doesn't really interact with the car. And maybe I want to move this down a bit more now. So I can select on this bottom face and make this a bit wider of an object. So I get a nice initial start to the spoiler. And now I've made my bigger movements, I can start making the more precise parts of it by changing up my cage size. So I can click on this, maybe the 24. And here now I can really start kind of pushing and pulling again on different parts of this to maybe bring in the top part in closer and leaving the bottom sides a bit wider. I can also bring in different parts like this in so they fold into one another, adding some kind of lip to this design. Or I can even bulk grab parts. So this bottom face, I can select on multiple parts of it using the control button. You see I got a couple of these now, and then I can push these all in together just to make sure that they're all uniform with their movements. And really quickly, in just a few button clicks, we're starting to get something that represents a spoiler, something that could be an initial design. Maybe I have to pull this up just a little bit more because I can see that it's intersecting with the car and we don't really want that. So I can do something like this. And there we go. This is, starting to look like something I would be able to throw into SOLIDWORKS to begin a test. And if I were to change this cage size, we can get a better idea of how it looks. And I mean, is this something that you'd really be able to model in SOLIDWORKS pretty quickly? Not really, because of, again, how smooth these transitions are. And if I want to make this, we still see some of these surfaces, I can always increase this to make it even smoother. And now we get something like this where it's an extremely smooth design, no bumps or anything like that. And still giving me that ability that if I find that maybe there's a side that doesn't look right, I can just push and pull that cage again. So really quick on these designs. And at this point, we're ready to go. I can now take this out, bring it into as a mesh, bring it out of freeform. But we were talking about how it works best in SOLIDWORKS to have solid bodies. And we've just been talking again and again about how hard it is to make these different kind of organic shapes into a solid. So how are we going to do it with this bracket? Well, with all of the designs I made, I used a tool called AutoSurface inside of Geometric Freeform. And what AutoSurface does is it's going to lay out a patch of spline lines over this automatically and then stitch them together to make surfaces, or stitch these spline lines together, creating a bunch of surfaces. And then these surfaces are going to be stitched together to make an actual solid. And how that option is used is I can just go right down into here, right click this design 5, and then we have auto surface available. And I can choose the geometry type and so on, how exactly I want this to be laid out. And when it's good to go, I can just click OK. And to save some time, I'm just going to say exit out of that for now and just bring it back into the PowerPoint, because our next slide is going to show off some of these designs. So here we are just talking again about that conversion from the mesh into a solid. And we can pull up this organic mesh that we've just carved out. And using the auto surface, we turn that into the solid body. And then all we have to do now is just, again, export out this solid as a parasolid or a step body, whatever have you, and it retains the XYZ information. And this is something that was really handy when it came to this rapid prototyping design, is because there's a lot of times where I will export out a model or a mesh, bring it into a different software and find out that it's not in the right position, and I have to figure out where it is in the XYZ space. Whereas in freeform, it retains all that information during the export. So I can take that mesh that I turned into a solid out as a parasolid, bring it into SolidWorks as an imported body, and it knows exactly where it is, so I can automatically align it to the car. And we can see that right picture, exactly how those NURB surfaces are laid out and stitched together. So you can see how we took that one really organic shape, made a bunch of spline lines and stitched them together, and we get something like that bottom right picture as a solid body. So setting up the file for these flow sims, again, we made a bunch of designs using this freeform method. Just let our creativity go, just pushing and pulling, kind of just drink a cup of coffee, spend about 2 hours designing a couple different initial versions. I made, I believe it was 12 designs initially, and about 2 hours of just kind of letting my creativity go. And now I wanted to test them out to see exactly how well these designs work and what to expand upon for my future designs. So setting up the flow sim, I don't want to go too depth into the file prep because it really is as straightforward as it's going to sound right now. It is just a series of configurations. I have a bracket part file, or the spoiler part file, where I would take those solid bodies that I created from freeform, import them into SolidWorks. Again, they're already aligned, so all I had to do is combine it into the brackets themselves through a series of configurations. And then in the car file itself, I just have two parts. I have the imported car body and then the spoiler itself. And then again, a series of configurations makes it so that way in the car file, if I select design 3 version 2, well, it's going to reference the spoiler design 3 version 2 configuration, change it so that way that's the spoiler visible, and then it's going to go into my car file as well. So everything is all linked together, making it super easy to add new versions if needed. And then for the flow sim, it's really the same steps. I used the wizard. I went through the wizard's setup. Again, this is my initial time ever using simulation for this kind of situation. But the wizard was very straightforward and able to walk you through it. Once the wizard was set up, I have my mesh laid out, my object selected it through my component control. I then wanted to create a local mesh around just the bracket itself, or the spoiler itself. So that way I'm not spending so much time waiting on the simulation to run at a higher density for the entire car. It'll run at a low density for the entire car, but then give me a high density around the spoiler itself, where we really want that information. And then also after making the initial design, or the initial study, all I had to do was just clone it to all my different configurations. And it took all the parameters from that initial study and applied it to these different objects, or these different part file configurations. So in a way, if I ever wanted to add in a new design to this, a new bracket, I just had to open up freeform, make the object, bring it into SolidWorks as a configuration, and then just clone my case study to that. And then in pretty much 4 button clicks, I was ready to go for my next study. And simulation, the wizard, just to kind of show, again, this idea of talking about how easy it is, but not actually showing, let's kind of go through the wizard setup for a different design. So right now I have this configuration in my design one, this configuration version 4, and it's something I haven't set up the wizard for yet. I haven't set up a project for this. I have a huge list, but nothing for that. So I'm going to walk through the steps on how you really use that wizard to set up these flow sims. If I go up into the wizard tab, just going to load up the different prompt. And here I can name my project, so I can name this Design 1 version 4. I can also say use this configuration, so it's going to take all the parts from this configuration. If I choose a different one, it's going to change it up to whatever it is. But right now I just want to use the current one, and I can click Next. Here, we're just setting up our units of this simulation. So I'm going to keep it all kind of standard, meters, kilograms, seconds. My units just the same way as well, and I can click Next again. We're running a external flow sim because we're going to try and see how the air goes over it. So in the analysis type, I just have to click external. And currently our object is watertight. Watertight refers to the fact that there is no internal cavities inside of it. But just to be safe, I am going to choose exclude internal spaces just to be on the good side of it. And we're not going to apply any physical features to this as well. So, no form of gravity or anything like that. At this point, we can start typing in, or we can choose our gas that we want to have it go through. In our case, I'm going to choose up in the gases. We have, right here, air. So I'm just going to double click air for our fluid type. And it's going to take all the parameters of what air is as a fluid and bring it down into the characteristics. Again, I'm not going to really choose any kind of flow characteristics such as humidity because we're assuming kind of an ideal situation right now. This point, it's going to just ask for how the wall conditions are. I'm just going to click Next on this since we're not really studying any kind of moisture settings or anything like that. And now we're at the point where it's starting to ask, okay, what is the actual velocity going on here? And it's really handy, again, just to kind of drive home the fact that everything is already aligned to one another because it saves so much time making sure things are in the proper place. Now, I already know that my car is in the proper orientation and all future designs are going to be in this proper orientation, indicated by our coordinate system in the bottom left. Looks like our car is pointing in the positive X. So if our car is driving forward, its velocity is going to be in the negative. So I'm just going to change this to, maybe something like -60. And at this point, I just have to click Finish and it's good to go. It's going to set up that and the rest of it for me in the background. And now we have our outline of our mesh cage ready. So we can adjust this even further. The next thing I did from here is just making sure that my domain is in the proper size. So I can edit my definition of this domain. And, as you see, it looks like our car would be floating in space right now. I wish this was the Tesla car out in space, but right now we just got to bring that ground a little bit closer so we don't have too much airflow going under the car. And also this does help out just making, again, our simulations run a little bit faster because, again, I wanted to do a rapid testing. Don't want to have to wait for it to calculate all these different areas that aren't needed. I want this to be kind of streamlined for all my different designs so it's good to go. So I'm just manipulating that mesh size. Next thing we can do is we can add a couple of goals. So if I want to add in some kind of global goal of velocity, I can do that right in here pretty quickly. And it's going to pop up in my list of goals. I can also add that local mesh by right-clicking here and inserting local mesh. And it's going to pop up just an extra little window just saying, okay, well, what are the components we want to have as the local mesh? And I have this kind of extruded body right here as the selection that I can choose. So that way, again, I have this extruded body as encapsulating all my spoiler designs, so I can have that higher coarse mesh right there. The last thing we can also double check on is, again, those component controls. So I can just make sure that only the spoiler and the car are visible as my control. If I zoom in, we can see as I select different things, what it's actually referring to. So I can just make sure that only certain designs are selected, like the car and the spoiler itself. Upon clicking OK, we are set to go. We're ready to start running this mesh or start running the simulation to get our end results. So on to the actual results from here. We first did an acid test of just trying to see what happens without any spoiler. So just kind of let's see how the airflow goes over this without any kind of brackets added or any kind of spoiler added. And for a car made in the 50s, very aerodynamic. The smooth transition on the back makes it so the air kind of just goes right through it, what to be expected for a racing type car. So with this kind of knowledge, this is where, again, we wanted to come up with the idea of, can we add something that's really cool, but doesn't impede this so much? So the first thing I did is I added a basic spoiler, just something again designed using this normal extrusions and spline lines, just to see what happens if anything is added to this car. How does that affect the airflow? And these are the results we got. It kind of showed that these eddies are starting to form on the under part of this. So I use this kind of as a knowledge of, okay, let me think about these different factors before I actually start making my first 3 designs, like I mentioned, to just get a couple of different rapid prototypes out there. Just seeing how the airflow is disturbed with just any kind of addition. Well, the first design I made, so again, got my cup of coffee brewed, sat down and started sketching out some ideas. I did enough research to still not say I'm a spoiler design engineer, but something to kind of get an idea of how things will interact with the car if I make them. And I made this first unique design, and it looks like a bicycle seat. And the idea is I wanted to keep something kind of central to the center of the car, something that has a way of kind of morphing down a little bit. And I wanted to see if I have a deep uh, tail end, a kind of a tunnel at the top, or maybe just something that's flat and forward, how these are all going to interact with the airflow. And these are the results from that. So I found that the further away the spoiler was from the car, the more eddies started to appear. Looks like actually that design 3 or the version 3 had overall one of the best airflows. Very smooth on the bottom part, and we had just minimal eddies at the top where those bumps were being, where I added these kind of grooves at the top. So it's something that I can take into mind when I'm approaching my next designs of, okay, maybe closer to the car works, having something parallel to the back of the car doesn't work out so well, creates these eddies, and maybe kind of reduce the top part of the bumps to help out with airflow. Design 2 was something a bit more traditional. I wanted to see if we really extrapolate these kind of tail ends, what's going to happen to the airflow, if it's going to maybe peter off a little bit easier or start creating even more eddies. So this design 2, again, added them into SolidWorks, cloned that configuration or that simulation to these and ran them. And these are the results from that. Again, just kind of getting some ideas of what different forms of spoilers are going to do with this airflow. And in this case, I found that having something, again, parallel or pointing straight with the car or the ground, and then something kind of tailing up, both cause some issues. We have those biggest eddies on those, whereas something that was actually kind of forming with the car, something pointing down, had very little eddies under it. You can see that the airflow kind of goes under, but a lot of traction starts happening just around the bottom part of the spoiler. So these are, again, factors I kept in mind. Maybe a thinner design isn't the best approach. Maybe something pointing up or straight isn't really what I want to do. I want to kind of go, again, with this kind of curvature of the car. And this design 3, which is my favorite design, was something I was like, let's make something really unique with this free form. This is really, I really wanted to kind of show off a lot of these tugging tools, really adjusting that cage value to make something really big for big movements and then more precise for these different type of, I almost call it like the X-Wing design from Star Wars. It's got like these different parts of the wings going up and down. So something that just really looks unique. And the key idea is just how can these different angles maybe affect? Are we going to have some eddies forming in between these fins? Something that, really we'd only be able to see by kind of this tug and pull method and simulation running. And this is what we got. So I found that from the first 2 versions that it really didn't work out as well as I wanted. We're still getting a lot of these eddies, but version 3 actually came out really well. And it was one of the first versions I really got to see that airflow above the spoiler reduce the amount of drag. So we can see we have this giant blue airflow going over. So the velocity is a lot less pressure going on at the top of the spoiler. We also have very minimal eddies. In fact, we didn't even have any kind of deep red type eddies like before with this design. So this was a case of something that I thought was really free-form shape, really unique, maybe wasn't going to get the best results, gave me something that was actually really usable with that version 3. So with this in mind, again, I set all these first 3 designs out without really testing them. I brought them all into SolidWorks, did a batch run, and in a couple hours, I got all those results, and I was like, okay, cool. Let's take this knowledge and apply it to a new version of a design. So I opened back up Freeform, made this design for saying, okay, that Y design, what I thought was going to be really unique, actually turned out pretty well. So maybe a wider design works. These channels at the top, either it being super smooth or this kind of flow at the very top to push the air through, also helped out. And also having the spoiler go with the curvature of the car and lower to the car helped out too. So just kind of taking bits and pieces from those first three designs, kind of hodgepodging them together, extrapolating, making them a bit bigger in certain spots, just to see what happens with this design for. And this is a scenario where I think we've all encountered where we thought, hey, let's take the best of all these different designs and then kind of make them bigger. Turns out it actually backfired a little bit. From what we can see from the first two designs, the eddies actually started wrapping around to the top of the spoiler. So I thought, hey, bringing the spoiler closer to the car would help out, when in actuality, it just caused the eddies to kind of go on top of it. We can even see that a little bit with the design 3. It's not as bad, but we can see it still wrap around when we do this roll by of the simulation. I did find, however, that with this design 4, that the airflow was actually really good in all three of them. So maybe we can keep this in mind and saying, hey, this wider area made it better for the top part of the flow, but worse for the bottom part. Maybe we just need to focus now on that bottom section of it, maybe making it a bit thicker or mirror off the car, have a different kind of tail end. So again, using this rapid design method of something that we don't have to invest too much time into the actual design part, we can really just kind of play around with some ideas and then run it in through simulation to see the end result. And to really drive this home, we made this last design right here. This, what happens if we put a spoiler only over the license? So at this point, it was already a week and a half done with all these first designs. We were kind of typing it up. We were talking about what to do next. What should we kind of, start writing about? And we came up with this idea of, hey, with that initial test, we found that the airflow really had issues only around the license plate. So what if we make a spoiler only over the license? And within 30 minutes, I was able to have a finished design inside of SolidWorks. These three designs only took about 5 minutes to make, and then it only took about another 5 minutes to bring it into SolidWorks and create those configurations. And because it was a pretty simple design, the simulation also didn't take that long. So in the same phone call of talking about making this really organic spoiler design over a license plate, I was able to actually show saying, hey, actually, I'm finding that this might not be the best method because it looks like we're creating more eddies specifically around the license plate. We're not really improving that much about anything else, maybe except for a little bit of the top airflow. And this, again, kind of drives home that idea of initial design where we kind of think of these cool ideas. Maybe we invest a lot of time into the design aspect of it just to find out that it didn't work out that well. Well, instead of having to spend a lot of time in the design side, and just to find out that it didn't go anywhere, in about 2 hours time, we went from nothing to a finished simulation just to see exactly how well that design works. So I thought that was something really, really cool, just to drive home that idea of rapid prototyping and organic shapes. So I just want to do a quick overview of this entire workflow because I'm kind of, talking about all these different results, and there are a lot of pretty gifts, but how about just kind of dialing back a little bit? So for the overview again, we created our new designs in freeform using that sub-D sculpting tool. So being able to just insert in the sub-D model, push and pull it around. We converted that sub-D mesh into a solid body using the auto surface inside of freeform. So that way, we don't have to worry about how do we actually make this thing now that we have it in a mesh form. We can just click a button and it turns it into a solid. We take that solid, insert it into SolidWorks itself as a configuration, and then we cloned our study to that new configuration in our flow sim. And then we just had to mesh and solve it in a batch mesh. So kind of 4 steps, and it really is that simple. And in fact, it's actually kind of like just 3 button clicks with the importing in and cloning this the mesh or the simulation itself. So it's a very straightforward process. It's something that really kind of caught me off of just how easy it was to kind of get this going for someone who's never really used FlowSim before or never really created a spoiler design. It's sometimes having that less knowledge on the design lets you have that more creative freedom. So it's fun to get this into the hands of people who've never really used it. But let's actually take it a step further. So not only can we use SolidWorks simulations to test out our designs, but what about creating some really cool organic shapes of the bracket itself? And we can do this using static studies. So we've been talking about this FlowSim idea of being able to use FlowSim to import in our meshes or solid bodies into SolidWorks again. But if we've already designed something like a bracket, we can already use tools inside of SolidWorks without needing to bring it back into any kind of sculpting software. So static study allows us to lock down a fixture in different spots. So in this case, I use the hinges to add in bolt locations and a virtual wall to replicate where the car would be for this bracket. And then I applied some stresses and strains to it. And with that, after applying a couple of the initial setups, I'm able to run a simulation really quickly. And I just want to tab back over into SolidWorks just to kind of show that bracket itself, so you can see the different design. So you can see it is really just as it is a solid body I created. This was the reference bracket I used, and in the static study tab, there we are. In the static study tab in simulation, we can add in all these different forces. And we use I use the forces created from the flow sim. So I found which design might have been the best. How are these forces applying in the X and Y or X, Y, or Z, just like a normal, if our bracket was sitting on the car and had the spoiler on top. And with that, I was able to kind of get this quickly set up. In the new study tab, just click on new study and then click on static, and this will set up the static tab where I can then add in kind of fixed hinges and the virtual wall to really set up the locked positions and the forces applied to it. And with that, we get a color map of seeing how the displacement is, and how the forces go through our bracket. And why I say we can take this a step further is because that static study turns into a topology study. Topology is this idea of, expanding upon what Ian was saying also earlier, where do you want to reverse engineer that initial brake lever that was topology optimized? It's really tough because the computer used some automation to know, based off of, forces applied, what can and can't be removed. So the topology study, we just have to take that static study after it's done. We see our displacement, looks like it's good to go. It's not going to break, and just clone it into a topology study and say how much material you want to reduce. So we can just get something like this picture on the right, where I've removed 70% of the material of the bracket, of the main part, based off of those forces applied. And I can use that now for future designs. So I can take that topology study and maybe recreate some kind of 2D sketch over it, using that as a reference to get something like the bottom right. Or I can take that mesh, either the topology itself or that recreated object, with the 2D sketches, export them out and bring them back into freeform. Once it's brought back into freeform as a clay model, we can start using some sculpting tools versus that sub D, and really just, that's truly where the creativity flies, that ability to just get a little pen and carve out different parts of it, optimize it in different ways that normally SolidWorks would not be able to do, because again, it's through a series of spline lines or tangential connections is how you can get that going. Whereas in freeform, it's just tugging and pulling with a haptic device, and you can kind of feel that instant feedback right away. And with that, I want to bring it back over to Ian. That was the case study, and if he has any closing remarks, I'll let him take it away.
All right. Well, I learned a lot in this study. Hopefully you guys can see my screen now. I have my contact info up, so that if you guys have questions that we don't get to today, or if you want to see a demonstration in more depth, reach out to me. I definitely want to hear from you. One of the things I learned in this whole thing is that I don't need to be scared of CFD, which I'd always been intimidated by CFD. I always thought of it as this really complex process that required someone with a PhD to do. And I learned that, yeah, there are more in-depth tools we can bring to bear, like Simulia, but that creating simple CFD studies that can help me guide a design process is actually really easy and not anything to be intimidated by.
Yes.
Another thing that surprised me in exploring some of the more traditional form factors we first looked at, most of which we didn't get a chance to show here, was just how mediocre most of the designs on the market are. It turns out that until you get into the highest echelons of design, most of the spoilers and race wing on the market are apparently just for looks, and in a lot of cases actually decrease efficiency rather than improve it. And ostensibly that's because they're considered hard to design. And like so many objects, they've been optimized for design limitations instead of being truly optimized for the function they serve. But as you see, creating designs that are actually good at the function they serve doesn't have to be hard. As you saw by the time elapsed in these designs, it definitely isn't hard when you identify the right tools for the job. So if you want to see more of the actual design process using freeform, including those interesting sculpting capabilities I talked about, again, go to the Hawkridge website, Resource Center, right at the top of the main page, and look for that webinar on duplicating organic shapes. There's also a bunch of other webinars there on more mechanically focused reverse engineering and inspection. So check those out if you're interested in some of the more common uses of 3D scanning. But if you have questions, if there's something you want to see in more detail, we have some time for questions now. You can also come talk to us afterwards at the digital 3D scanning booth. If you don't have time for that, again, my info's up on the screen. Screenshot it, jot it down. If you have questions, I want to hear from you. So thanks for your attention, and we'll go ahead and open it up to questions.
Yeah. And, while we're waiting for the questions to come in, I really want to kind of emphasize more of this idea of just allowing the creative freedom to kind of sculpt and freeform design different parts. It's because we are, with the addition of 3D printers becoming more and more popular, there are other tools for reverse engineering, but it's really hard to get the really organic, hand carved aspects into our models, I feel still. And that's something that really with freeform I wanted to kind of emphasize with especially that 7D modeling, how you don't have to have a CAD mind or CAD knowledge to start designing with some of these tools. As you saw, it was kind of like clay pushing and pulling. Anything that you can do with a clay ball, you can do inside of freeform. So it really, it opens up this idea that there are other parts, and possibly in your department or in your company, that might have someone who's really good at that kind of clay modeling approach and not really in the CAD approach. And with these new tools, we can really bridge that, bridge the gap between this. So you can have a lot more interactive prototyping coming up in the future. So it's just something I really, I thought was really cool about this project. And again, I want to just reemphasize that.
Yeah, I felt the same. One of the things that really struck me was like when some of those spoiler designs where they were kind of zany and we were kind of just having fun, and how some of the most unexpected ones actually ended up being the best, and they weren't shapes that we would have ever set out to design, because we haven't seen spoilers like that on the market. And it was just really the freedom of design that this tool allowed us to just kind of wander around on paths not taken and come up with new concepts.
Yeah, and actually to even build off of that, there's a question that James just asked about entering into the X-ray tech for internals. And I just want to say that I haven't used it myself in that sense, but this freeform, this geomagic freeform software is heavily used in that because you can work with negative spaces to convert it into that clay form that I was mentioning in the very end. And you could take an X-ray of someone, get that internal space as a negative, and then turn it into clay. And then you have that now as a kind of mesh bulk body that you can push and pull on to design around as well. So it's definitely branching into that X-ray technology with those internal clay modeling approaches.
Yeah, and to further clarify, there are X-ray and micro CT solutions on the market for industrial use. And in fact, one of our good friends and customers, Delphi Precision Imaging in Redmond, Washington, they have a big industrial CT scanner, and they use Geomagic Design X to reverse engineer files from it. So, reverse engineering data from one of those X-ray or CT systems, it's exactly like any other kind of line of sight scanner, any kind of garden variety scanner. The approach is the same. You just have more data and you have the internal data without having to cut something apart. For the rest of us, there is destructive scanning, and this is commonly done in the automotive industry. And there's actually a blog on that on the Hawkridge website of scanning an enclosed impeller by sacrificing one and cutting it in half.
Yeah.
A few options there for scanning enclosed areas.
As for 3D scanning transparent parts, there are laser technologies that can start to scan crystalline glass and plastic clearness. But a lot of times we use something like a disappearing spray to add some kind of opaqueness to the clear object, and that makes it a lot easier to scan. So it really is dependent whether you have that ability to do something with a spray that makes it much easier for most 3D scanners, or you can use some kind of like high-tech laser scanner, like a blue light laser that can scan transparent objects. So it really depends on the situation and the technology you have at hand.
All right. Well, that's all the time we have to allow you guys to get to your next session. Again, use my contact info if you have more questions or want to see a demo on something specific. If you want a trial of one of these products to play around with, let me know. We're going to end it there, and thank you all very much for coming.